So there's several properties that have to do with intermolecular forces or are caused by intermolecular forces, but the two big ones are melting point and boiling point. All substances have a set-in-stone melting point and boiling point. We can look those values up, and at a certain pressure, they're always going to be the same. And the melting points and boiling points, relatively, are due to the intermolecular forces. So substances that have high boiling points have high intermolecular forces. Substances with low melting points are going to have low intermolecular forces or weak intermolecular forces. States of matter have to do with this. So gases, things that are gaseous at room temperature, that means they have very, very low boiling points and very, very low melting points. That's what makes them gases at room temperature, because they've already melted and boiled off. So as a result, things that are gases tend to have very, very weak intermolecular forces, whereas things that are solids or liquids tend to have stronger intermolecular forces. So we think of most ionic solids, okay? Ion to ion intermolecular forces, they tend to be solids at room temperature. Something like water with its strong hydrogen bonds doesn't boil until 100 degrees Celsius. It's because it's got those intermolecular forces holding it to a liquid. N2, which is gaseous, only has London dispersion forces. Those weak London dispersion forces can't hold them together, so they tend to be a gas at room temperature. So if we think of a substance that is at a solid state, so at the solid state you've got all of those molecules pretty evenly arranged, and you're going to have those intermolecular forces that are holding them together. So if this was water, it'd be a dipole, or a hydrogen force holding it together. If this was N2, if you managed to get it down to freezing point, it would be London dispersion forces holding it together. If it's sodium chloride, it's going to be ionic, whatever it is, holding it together into that rigid structure. So the melting point, we know what melting point is. It's the point where something goes from a solid to a liquid state. So what that means in terms of intermolecular forces is melting point is really just when the intermolecular forces between the solid particles are broken. So melting point is the transition from solids to liquids, but it's when we supply enough energy to break the intermolecular forces. So when something melts, its intermolecular forces are being broken. Therefore, something that has a high melting point is going to have strong intermolecular forces, and vice versa. Something with a low melting point has weaker intermolecular forces. And you know, something that's at a liquid, okay, in the liquid state, they still have the intermolecular forces interacting, but the energy that's supplied, more energy, more motion, is going to cause those molecules to kind of move around, and so the intermolecular forces are going to be constantly breaking, reforming, so they're sticking together but not stuck together. And so when we boil something, we're changing it from a liquid state to a gaseous state, which is the point where all of those molecules are separated and they're individual with no intermolecular forces. The boiling point is when we supply enough energy, once again, to completely break those intermolecular forces, so to separate them entirely from each other. And just like it was with melting point, high boiling points are going to indicate strong intermolecular forces. Low boiling points are going to indicate weak intermolecular forces. And things that are gaseous at room temperature, so things like oxygen or nitrogen, any other gas that we know of, those are all going to have low boiling points. That's what makes them gases at room temperature. So here's an example of a question you might be posed with. Which species has a higher boiling point? And we're given two choices. Now, when we look at ones like this, we have to compare things that are fairly similar in size in order to get a good representation. If we compare one thing that's massive, one thing that's small, there's going to be more things at play than just the intermolecular forces. So the first thing you need to do whenever you're posed with a question like this is first identify the intermolecular forces acting on each of the compounds. So not just one of them, but both of them. And in this case, C2H6 and C3H8, both of which are alkanes or carbohydrates. Carbohydrates, alkanes are always nonpolar. So that's a hint. Make a note of that in your brains. Anytime you see a substance that's composed entirely of carbon and hydrogens, it's going to be nonpolar. If you throw some oxygens in there, some nitrogens in there, that can change the game, but carbon-hydrogen compounds, always nonpolar. So both of these are nonpolar, and if we want to figure out which one has the higher boiling point, then we're going to have to figure out which one has the stronger London dispersion forces. And to look at that, we're going to have to look at polarizability. So the larger molecule, therefore, is going to have the higher boiling point because it's more polarizable. Larger molecules, electrons are spread out, it's easier to pull them to one side. If it's easier to pull them to one side, it's easier to induce a dipole, therefore it's going to have stronger intermolecular forces. And so since C3H8 is the larger of the two molecules, that means it's going to have stronger intermolecular forces, therefore it's going to have a higher boiling point. And then down here, these aren't numbers you'd have to calculate, but it's just given to kind of show us where we're at. Hey, what do you know? Negative 42 degrees Celsius, negative 89 degrees Celsius. So C3H8 does have the higher boiling point. So you can see both of these are going to wind up being gases at room temperature, though. All right, we're going to go through and answer a couple different questions about these compounds with the end goal of figuring out which one has the higher boiling point. So we're looking here at this guy, which happens to be ethanol, and this guy right here that happens to be propane. So the first thing we want to figure out, okay, are these polar or nonpolar? Because that's going to make a difference in what the intermolecular forces wind up being. So this molecule right here, it's not symmetrical. If it's not symmetrical, that usually indicates a polar molecule. And in this case, we have an oxygen bonded to hydrogen, and so that's going to have a situation then where the oxygen is going to pull the electrons towards it and create that kind of hydrogen bonding thing. And so this first molecule right here is going to be polar. C3H8, carbon and hydrogen only, which indicates that it's probably going to be nonpolar. Now that we've answered that, let's figure out what intermolecular forces are acting on both of those. So this first one right here, we've already said the electrons are going to be pulled towards the hydrogen. We've got that oxygen covalently bonded to hydrogen. That means this guy is going to have hydrogen bonds. So we'll just call them H bonds. This guy over here, which is nonpolar, the only thing they have is London dispersion forces. And hey, let's not forget over there, hydrogen bonds and London dispersion forces. So both of these have London dispersion forces, but this one also has hydrogen bonds. So then finally, let's compare the relative boiling points. So which one of these two do we think is going to have the higher boiling point? Yeah, it's going to be that first one. It's going to have the high boiling point. We know that because it's got stronger intermolecular forces. This guy's got hydrogen bonds. That little weakling's only got London dispersion forces. There's not much holding these molecules together. They're going to spread apart fairly easily. And if you're curious, the boiling point of ethanol is 78 degrees Celsius, whereas the boiling point of propane is negative 42 degrees Celsius. Propane, it's a gas that we use to power our gas stoves and things like that. Ethanol, that's used in like gasoline engines, and so it's a liquid. Okay, I want you guys to practice on these. So we'll go through them one question at a time. First thing I want you to do is pause the video and decide, are these polar or nonpolar molecules, and that's what's going to go in these two boxes. All right, neither one is symmetrical, so they're both going to be polar bonds. Next thing I want you to tell me is what types of intermolecular forces are going to be acting on these two molecules. Alright, so this first molecule, it looks a lot like our ethanol. In this case, it's methanol. And so it's going to have that oxygen to hydrogen right there, which is going to generate that hydrogen bond that's going to pull the electrons over towards the oxygen. And over here on this molecule, this is glycol, which is actually antifreeze. We've got one oxygen to hydrogen right there. Oops, sorry, it's going to be pulling right there. And then another oxygen to hydrogen right there. So we actually have two hydrogen bonds on that molecule right there. And then both of them, of course, have London dispersion forces, just like every other molecule in the world. Okay, so these both have essentially the same things acting on, same intermolecular forces. So the next thing I want you to pause the video and write down then is which one is more polarizable. Okay, so the guy here on the left, methanol, it's small, and so it's going to be less polarizable than glycol, which is big, which is going to make it more polarizable. And so all three of these can be used to help us determine what the boiling point is going to be. And we use that by indicating which has the stronger intermolecular forces. So now, finally, go ahead and tell me which one you think has the higher boiling point. If you said that glycol is going to have the higher boiling point, you'd be absolutely correct. And the reason for that is, number one, it's got two hydrogen bonds, so if we double the amount of hydrogen bonds, we're doubling the amount of strength right there. Also, since it's larger, it's more polarizable. Electrons can be pulled easier to one side, which means its London dispersion forces will also be stronger than methanol's London dispersion forces. So as a result, glycol has a higher boiling point than methanol. And if you're curious, the boiling point of glycol is 188 degrees Celsius, whereas the boiling point of methanol is a mere 66 degrees Celsius. Okay, walk yourself through this one. We're looking at melting point in this case, answering the same four questions. So polar, nonpolar, what types of forces, polarizability, and then finally boiling points relative to each other. Sorry, melting points relative to each other. Alright, so we're comparing here methane and carbon tetraiodide. Both of them are going to be nonpolar. They're going to be tetrahedral shapes, and they're going to be symmetrical tetrahedral shapes, which means there's going to be no pulling of electrons to one side or to other. And as a result of both being nonpolar, both going to have only London dispersion forces acting on them. So now we need to compare size. And so methane is smaller, which means it's going to be less polarizable than carbon tetraiodide, which is larger, more polarizable. As a result, then, carbon tetraiodide is going to have the higher melting point than methane. And it's because it's got London dispersion forces that are going to be slightly stronger than methane's. And if you're curious, the melting point of carbon tetraiodide is 171 degrees Celsius. The melting point of methane, negative 183 degrees Celsius. So that mere difference in size makes a difference of 400 degrees Celsius between these two boiling points, or melting points. Okay, final one, type of bond, type of intermolecular force, and then relative boiling point in this case. Sodium chloride, of course, has ionic bonds, whereas water has polar bonds. So as a result, sodium chloride is going to have ion-to-ion intermolecular forces, and water has hydrogen bonds. And although hydrogen bonds are really strong, they're not stronger than the ion-to-ion intermolecular forces. Therefore, sodium chloride is going to have a higher boiling point of 1,413, and water we know has a boiling point of 100 degrees Celsius.